This is a recording for pre-calculus, and this is section 6.2, the law of cosines. And our objectives are that we want to be able to use the law of cosines to solve oblique triangles where we know the side, three sides, or side, angle, side, two sides, and an included angle. We also want to use the law of cosines to model and solve real-life problems. And finally, we want to use Heron's area formula to find the area of a triangle. So let's start with the law of cosines and kind of an introduction. The two cases that remain are side, and side angle side, when you know all three sides or two sides in the included angle. And when you have those situations, the law of sines does not any longer work. And so instead we can use the law of cosines. And so maybe if we covered this in the past, or you've looked at this in the past, we generally look at this version, c squared equals a squared plus b squared minus 2ab cosine c. You'll notice that whatever side you start with, whether it's C, B, or A, you end with the cosine of that angle that is opposite that side. And then the other two sides are represented with squaring and minus 2 times those two sides. Also notice that, you know, if it's a right triangle, you actually can see the Pythagorean theorem in there as well. And the alternate form, and so, you know, I don't know, I just gravitate to this one. The alternate form there is the cosine of C equals a squared plus b squared minus c squared over 2ab. And I'm just going to tell you that I usually don't use exactly that version. Sometimes I do, but I don't always remember it. But usually I kind of think in my head, this version I know, c squared equals a squared plus b squared minus 2ab cosine c. And sometimes I have students just kind of solve this, and for the cosine of c, if you think about what you would do, you would subtract a squared and subtract b squared. So that gives you c squared minus a squared minus b squared equals negative 2ab cosine c. And then we divide by negative 2ab on both sides. And that gives us c squared minus a squared minus b squared all over negative 2ab equals cosine capital C. So if you compare this version to kind of the version up here, you'll notice my c squared is positive, the a's and b's are negative or subtracted in my version, and you'll also notice, I'm going to just write that minus a little better because I feel like it didn't quite look that way. And because I'm dividing by a negative. So if we multiplied everything by negative 1 over negative 1, we would get, and I'll rearrange it as I go, a squared plus b squared minus c squared all over 2ab equals cosine c. Also, that also means that capital C is equal to the inverse cosine of a squared plus b squared minus c squared all over 2ab. And there's a lot of patterning going on there as you look at that, and there's also, it's very parenthesis intensive if you're using a calculator as you go. So make sure you pause this if you need to write down these versions of that. You know, go ahead and write all 6 of them, but then you want to kind of really focus in on the patterning as you go. Moving on. we're just going to look at a couple of examples here, and it says find the three angles of the triangle shown below. Now, one thing I'm going to tell you is we're going to use the law of cosines, because think about the law of sines. We would have to know or be able to find an angle and a side opposite that where we would know both of them. And here we have no angles at all, so we can't do that. And also think about when we do all students take calculus. So from 0 to 90 degrees, everything is positive. From 90 to 180, sine would still be positive. That's why it always defers to kind of the acute angle, but cosine would be negative. And so if you always find that largest angle first, then if you defer to the law of sines, everything will work out because it'll give you acute angles. So make a note to yourself that when you're given all three sides, you should find the largest angle first. And truly, it doesn't matter which side we have, but let's think about this, and we'll use the version that says cosine B equals a squared plus c squared minus b squared all over 2ac. And so capital B equals the inverse cosine of, and then a is 8 squared plus c is 14 squared minus 19 squared over 2 times 8 times 14. So actually, you know, that's a little calculator intensive. So go ahead and use your calculator, pause this, and see if you can find B maybe to 2 decimal places. Okay, let's see what we got. The answer should be 116.80 degrees for that one. Now, you can either find all three angles using the law of cosines, and if you do that, first of all, if you've made a mistake, you're not going to get caught in that mistake. But a lot of times we want to defer to a different law because it might be easier. So once I know that that angle B is 116.80 degrees for that little angle right there, then I can now defer to the law of sines because I now have an angle and a side opposite where I know both. So if you want to, you can do that. If you want to use the law of cosines for all of those, by all means, go ahead, and that kind of is your more guaranteed method. But because I'm talking about it, I'm just going to use the law of sines now. So 19 over the sine of 116.80 degrees equals, we'll do 8 over the sine of capital A. And so that means the sine of A is 8 times sine 116.80 degrees divided by 19. And so A is the inverse sine of 8 sine 116.80 degrees divided by 19. This is much easier to type in on a calculator. If you want to try that, go ahead, pause this, and then we'll go over it. Okay, and we should have gotten that A is 22.08 degrees. And, you know, likewise, we can now find C just using the fact that the sum of the angles of a triangle is 180 degrees. And so we can say that capital C is equal to 180 minus parentheses 116.80 plus 22.08. And so C is approximately equal to 41.12 degrees. That should have been approximately as well. Now, keep in mind, you know, all these different methods, you know, we just have to be cautious as we go through these problems. And again, you could just use the law of cosines for all three angles, and that would be fine. Now, moving along, this kind of goes over the reminder that suppose for a minute that we'd have found maybe sine A, which is 22.08 using the law of cosines. Then when we tried to find B, capital B, the law of cosines, because cosine is positive in the first two, or because sine is positive in the first two quadrants, if we had deferred to the law of sines after we found an acute angle, um, it'll give us an acute angle for that other one. And our angles, always just do a little extra checking. And of course, the way we did it, of course, they added up to 180 because we used 180 minus the other two. But always just kind of give yourself a little check if that makes sense. So remember that the cosine of theta is greater than 0 in the first quadrant between 0 and 90, and it's less than 0 between 90 and 180. So once you found that B was obtuse, you know A and C both have to be acute. And if the biggest angle is acute, then the other two angles also have to be acute as we go. All right, now the next one says find the remaining angles and sides of the triangle shown below. And so for this one, do we know or can we find an angle and side opposite each other pair? And I only have this angle, so I would have to have that side. So the answer is no. I have to use the law of sines, or excuse me, cosines for this one. And then I want to kind of think about how to approach this once I find that side. So let's use the law of cosines. A squared equals, because it's a little a that I'm going to find, equals b squared plus c squared minus 2bc cosine capital A. So A is just the square root of all this, and that'll be 9 squared plus 12 squared minus 2 times 9 times 12 cosine 25 degrees. And again, this one's not too bad to type in either as you go. And so take a minute and get that maybe to 2 decimal places. And we should have found that that is 5.41 meters for that one. And I think I wrote below that it's also 5.4072 as we look at that, just to kind of know. Now we have to kind of think about our plan. So I'm going to go 5.41 meters. Now I can use the law of sines, but I have to kind of think about the fact that that side and angle that I know are not the largest one as we go. And so we want to look at this in a very careful way. So let's proceed by kind of using the law of sines and kind of see what happens. And we kind of have to think about reference angles and things that are happening in the shape of this picture as we go. So we can now say that the sine, that 9 over this, oh, I'll start with the one I know, 5.41 over the sine of 25 degrees is equal to B over the sine of capital B. So if we go about it this way, and I think I'm going to use my 5.4072 just to have a little better decimal. And so that means that the sine of capital B, oh, excuse me, I'm missing something here. Little b, which was 9. My apologies. So the sine of b is equal to 9 sine 25 degrees over 5.4072. And so then that means b is equal to the inverse sine of 9 times the sine of 25 degrees over 5.4072. Take a minute and find what that is. And you should have gotten 44.7 degrees is approximately what B is. But we also kind of have to think about this. Remember that when we do this, all students take calculus. If it's 0 to 90, it would be 47. But suppose the reference angle is 44.7. And that means it could also be there and be an obtuse angle. And so we want to say, remember that there are two angles whose second angle is who fit this. I'm sorry, who fit this. And so let me, so there are two angles that fit this situation. And so it could be this 47 point or 44.7, but it could also be if I draw in the other angle here with that reference angle of 44.7, that would give us that 180 minus 44.7, which would equal 135.3. But notice if we use that one, so we do have to do a little thinking here. If this were 135 degrees, 12 is the biggest side. So, we can't have more than one obtuse angle, so it has to have the biggest angle. So this one doesn't work, but the reason I point that out is suppose we had used the 12 and C, then we would get with the law of sines the acute version, but we would need the obtuse angle there as we go. So in checking this out, the measure of angle B is 44.7. And so then we can find the measure of angle C. And let me see, capital C will be then 180 minus 44.7 plus 25. And so capital C is approximately 110.3. Degrees. And so there's all of our parts that we kind of had to find. Now, you can avoid having to figure this little deal out. You can avoid this whole situation and having to figure that out by just using the law of cosines for everything, because the law of cosines and finding that maybe biggest angle next, and then you'd get that obtuse angle right away. But do be cautious when you're doing these law of cosine problems. Now, our next problem is an application problem, and here it is. The pitcher's mound on a women's softball field is 43 feet from home plate, and the distance between the bases is 60 feet as shown in this little picture here. The pitcher's mound is not halfway between home plate and second base. How far is the pitcher's mound from first base? Now, the first thing I'm going to say is when I look at this, I'm like, oh, 45, it's a 45, 45, 90. But it is not necessarily. We do not know that that's a right angle, and if that is not equally distant, then it is not a right angle. So I would maybe just draw this picture for number 3 of the triangle. So the things that we know, this is home plate, this is first base, this is the pitcher's mound. This is 43 feet and that's little f. This is 45 degrees. This is little p, and that is 60 feet. And this is little h. And so little h is what we're trying to find as we go. And so think of the pattern of the law of cosines. So little h is equal to the square root of little f squared plus little p squared minus 2 times f times p cosine capital H. And so then we can just kind of plug in those things. H equals the big square root of 43 squared plus 60 squared minus 2 times 43 times 60 cosine 45 degrees. And then just kind of using what we know to kind of figure that out and typing that in our calculator and see what you get for H. And we should get H is approximately 42.43 feet as we go. So, you know, it's not exactly a 90-degree angle, but it's pretty close as we look at that. So our next problem is going to be another direction and bearing problem. So, you know, after our last exam, I'm just going to remind you that for ships, bearing is north or south first, then east or west second, and it's always, you know, north so many degrees east or north so many degrees west would be that angle, south so many degrees west or south so many degrees east. So just kind of keep that in mind. That's the bearing part. And this one does give us the picture, and I'll just read through it. So a ship travels from A 60 miles due east, and so straight east. Then it adjusts its course. So this is our north arrow, it could be right here. And it goes 80 miles in this new direction. And then it's 139 miles from the point of departure. And from B to C, we want the bearing as we go. And let me kind of get rid of all that. And so really, we want to figure out some angles here. Maybe angle B is the angle that we want to find. We know this will have that, you know, kind of 90 degrees, so it'll be right there. So then this little piece will be the rest of that bearing. And we definitely are going to use the law of cosines. So we'll just remind ourselves the cosine of capital B equals a squared plus c squared minus b squared all over 2ac. And so B equals the inverse cosine of, and little a is 80 squared plus 60 squared minus 139 squared all over 2 times 80 times 60. Probably I wouldn't write those in parentheses as I was typing them in. Take a minute, pause this, and see what you get. Okay, we should have found that this is 166.15 degrees. So keep in mind that's that whole angle B right there. But we want to think about our kind of north star kind of here. So we're going north, and then from north, we're going to go towards the east. So we're going north something and then east. And we also want to think about the fact that there's a 90-degree angle here, and this whole angle right there is 166.15. So our number that's going to go here is 180 minus 166.15. No, I'm sorry, that is very wrong. It's going to be 166.5 0.15 minus 90 degrees, that right angle that I just talked about. I don't know why I did 180 then. And that is going to be 76 degree, 0.15 degrees. And so we're going to go north 76.15 degrees east as we look at that. I do have another problem for you to try. If you want to go ahead and I'll pause this and then we'll see how you did. So let's see how you did on this one. And oops, let me there we go. There's our formula. So B equals the inverse cosine of 30 squared plus 40 squared minus 56 squared all over 2 times 30 times 40. So B is approximately 105.37. That's north something and then east. And we do the 105.37 minus 90. So our new bearing is north 15 degrees 37 or 15.37 degrees east as we look at that. So the last thing is Heron's area formula. And to be super honest, this is one of the most asked for formulas in my own personal life. We've had family and friends ask us this question. They're doing a home improvement project, they're putting in a garden, blah, blah, blah. They're doing some little project, and they're like, I know what the 3 sides are, but I don't know what the area is. And this is the formula that I always tell them to use is Heron's area formula. And if they didn't have a pre-calculus class or they don't remember it, then they don't know Heron's area formula. So the law of cosines can be used to establish this area formula, and it's called Heron's area formula after a Greek mathematician. You know, many formulas and theorems are named after mathematicians. So here it is. Given any triangle with the side lengths A, B, and C, the area of the triangle is area equals the square root of S times S minus A times S minus B times S minus C, where S is A plus B plus C divided by 2. I will just tell you the common mistake people make is, they want to find the average of those and they divide by 3. So take a minute, pause this if you need to, write that down, and then we'll look at an example. Okay, moving on, and also kind of think about, since S is adding these 3 sides and dividing by 2, it's not going to be a horrible number for us to use as we go through these problems. So find the area of the triangle having side lengths. A is 43, B is 53, and C is 72 meters as we go. So we're going to first remind ourselves that S, and I usually write it in a cursive. So 5A is 43 meters, B is 53 meters, C is 72 meters, and find the area. And so we're going to find S first. It's 43 plus 53 plus 72, all divided by 2. So S is equal to, that will be 168 divided by 2, so that'll be 84. And then the area is equal to the big square root of S. And notice I use a cursive S because that's the only thing I don't like is the writing S as a variable. S square root of S times S minus A times S minus B times S minus C. And so then that is the big square root of 84 times 84 minus 43 times 84 minus 53 times 84 minus 72. And then really you just type that in your calculator and see what it gives you. We will round to 2 decimal places, and so the area is approximately 1,131.89 square meters. meters squared as we look at that. So that is Heron's formula for area, so it's pretty straightforward. Really take a moment, write some things down for yourself about this. We now have 3 ways to find areas of triangles. That old standard way you probably learned in junior high or at some point much earlier in mathematics. The oblique triangle, that's kind of using the law of sines idea. And then Heron's area formula, which is this S1. And then it doesn't say on this handout, you know, but we would add where S equals A plus B plus C divided by 2, just to kind of know for sure what that is. So this concludes 6.2, using the law of cosines to solve oblique triangles, side, 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 or side angle side. Use the law of cosines to model and solve real life problems, and use Heron's area formula to find the area of a triangle. That concludes the law of cosines.